Thank you, Yuda, for giving me the courage to stop and redo this. This will be much easier for me. So how do we implement this idea of having original circuits and then a check circuit that that implements this trapdoor? So what I'm going to do now is I'm going to walk through all of the syntactic components of. So I'm going to just give you the protocol, exactly how it works, and try to explain intuitively how all the pieces fit together. Now, much of the motivation for why all of these things are done in this particular order comes from the security proof, which I won't go through. It's just not a proof that one can. It's not a proof that I think one can explain to an audience. One has to understand the intuition for how this works, and then carefully look at this hybrid experiment to see why things are done in this particular order. I'll try to give some motivation for why they're done, but just to get involved in this research area, you can sort of see the high-level ideas and try to see their motivation. So to get right to it, how do we implement something like this, and why does it work faster? So the first step that Alice takes in this is preparation. So what she's going to do, she's going to think in her head of some garbled circuit. In particular, she doesn't have to think about the whole garbled circuit. What she has to do is think about the first level input wires to this circuit. So what she's going to do is pick a set of elements from some group. So this protocol, it's described in a way that works in a with specific number theory assumptions, like discrete log assumptions, to make it all work out. So imagine she's going to pick these two elements for every one of her input wires from some group G, some discrete log group. And then she's going to, at this point, commit to those keys for those input wires. She's going to compute this G to the AI times some RJ, and G to the A1 times some other RJ, and she's going to compute some commitment, which is some sort of, you can think of some efficient way of doing it is sort of hashing, like a good hash function gives you statistically hidden commitment. So she's going to pick, she's going to set those keys and remember these things. And then at the top of the circuit, what she's going to do is select some random labels for the output wires. And in particular, for every output wire, she's going to select a particular B0 and B1. So for the ith output wire, she's going to pick some specific labels for that, for those output wires. Okay, that's her preparation. And now once we have that in mind, we can then define how this check circuit is going to work. So right now I'm just describing how these garbling circuits work, and then I'll explain how the protocols work. So we have the circuit here on the left. All we care about are the input wires, A's, and the output. The input wires, the labels for which are determined by A here, and the output wires, the labels for which we've chosen B for. And now this check circuit is going to have these B components. So this is a check circuit for, let's say, the ith wire. And it's going to have these B wires hard-coded into that check circuit. Okay? And so the circuit logic is going to be very simple. If Bob can supply two of these witnesses, so if Bob is able to give both B01 and B0 and B1 for this ith output wire, then the output of the circuit is going to be X. Okay? And and of course the circuit can have the B's hard-coded, so it's just a very simple check right there. And intuitively, the protocol that we're going to run for this check circuit is going to be a standard maliciously secure computation. So we haven't described one yet. You got an idea for how to make one in the first half of this. We'll go through a more specific version later on, but this will just be a standard secure computation. The crux of the idea is that we can afford to do a more expensive standard computation on this circuit because algorithmically, why will we come out ahead? Because this circuit is going to be very small. It's going to be on the order of n plus k gates, n being the size of the input and k being the size of the security parameter. So this is going to be a small circuit which will repeat like 120 times to get the security. This will be a big circuit, arbitrarily big, for which we'll only have to repeat k times. And that's how we'll win. And now you can already do the equation in your head for when this approach wins out. You can balance the two, and this thing has to be sufficiently larger than the addition of that. Okay? Now, two other points. Remember, we're going to be using cut and choose for this part of the protocol. Okay? And so an important thing is that when we do a cut and choose, the evaluator is going to get both B0 and B1. Okay? So we have to be careful when we organize this protocol to make sure that the inputs that are used in this check circuit don't come from the B0 and B1 that are from cuts. Okay? And so, right, because after this guy does a cut and checks, since we're using B0 and B1, the same Bs for every single copy of the ith output wire, after a cut, the guy will get a witness. So we just have to be careful to make sure that we argue that, in fact, this is not the witness he's using. Right? And the other important consideration we have to make is to ensure that the input that's used, the X input, the generator's input here is X. We have to make sure that the same X is input here as it is input here. Okay, now, what is that problem called? Input consistency. We've already solved it in the previous overview section. We knew that whenever we do cut and choose, we have to make sure that the input is used in every copy of the circuit. Now, earlier, we had argued that we had a protocol, some sort of vague notion of a proof, to make sure that the same input is used in every single copy of the circuit. Now, there's nothing in that argument that prevents you from using the same technique to show that the same input is used in a different circuit. Okay, so the same idea for doing input consistency will apply here to make sure that the inputs between this check circuit and the original circuit are the same. And we'll talk about a specific version, how to implement that specifically, in particular here using this discrete log approach. Okay, so that's just an intuition for how this check circuit works. So let's go back to what the protocol is. First, Alice prepares all of these values here, the B's and the K's right there. Okay? And then Alice and Bob do an oblivious transfer. And this is a slightly bespoke oblivious transfer. It's going to have a special case here. So what are the inputs that Alice will put? So Alice is going to have a 0 input and a 1 input. Bob is going to have his bit as input. And there's going to be a special third case. So Bob can either put 0, 1 for if he wants input, or he can use this third input, the blue pill, and in that case Bob gets both of the input wires. This is so to say, Bob is then choosing to test that circuit instead of evaluating it. Okay, so this oblivious transfer works. It's like a cut and choose oblivious transfer. Is one way to describe it, and so Alice is going to input Bob's input keys, 0 input keys here, 1 input keys there, and then both pairs of input keys in this third case. Now there's one other variable that's important to talk about here, and this is the string called chi-j. Okay, chi-j is a secret string that Alice is going to choose here, and she's going to only include it on the oblivious transfers where Bob either gets the 0 input or the 1 input. Okay? And this special string, chi-j, is what we're going to use to solve this problem right here. Remember, we said that we need to make sure that the witness that Bob uses in this check circuit can't be a witness that he receives from the cut when he cuts a circuit. Okay, and so this chi-j is going to be exactly that. This Chi-J is to say, here I have a 0 input for a circuit that I evaluated, and I have a 1 input for another circuit that I evaluated, if you have the same Chi-J. Okay? So at the end of this cut and choose, right, so these were Alice's inputs. Bob's inputs are going to be, as we described earlier. Bob is going to select a challenge set. How did we pick that challenge set before? 3 slides ago, yes. Uniformly pick a subset over all of the K. So just some subset, uniformly over all subsets, and use those bits to either get the input if you're going to evaluate that circuit, or get these input wires if you're going to check that circuit. So at the end of this step, one can basically say that Bob has 2 outputs. For all of the things in his challenge set, he has both of his input keys. And for all of the things outside the challenge set, he has his input key and the special Chi-J string. And now, how I'm going to describe this protocol over the left is, this column will be all the stuff that Alice accumulates during the protocol. This column will be all the stuff that Bob accumulates over the protocol. And the middle will be roughly what happens. Okay, so the next step is that Alice is going to commit. She's going to basically send several commitments. And the first commitments are going to be to the output wires. Remember, B0 were the strings that, these are the output labels for all of the output wires of the circuit. So Alice is going to commit to all of those. For each of the output wires, she's going to commit to a hash of these things. Next, she is going to commit to the AIs that she uses in order to pick the keys for her input wires. She's also going to commit to the randomness that she uses to compute that. So she's got the AIs here, and she's also going to commit to this RJ. And finally, she's going to send over all of her garbled circuits. Okay? So, as you can sort of see, these are all the things that Bob will accumulate on the left here. Okay. Now, Bob is going to send over his challenge set. And in particular, so he's going to say, J is my challenge set, and the Chi-Js, the things that are not in my challenge set, are the things that I'm actually going to evaluate. Okay? So he's giving a witness for all the things that he's going to evaluate. And then Alice is going to send over, for each of the things that, for each of the circuits that will be evaluated, Alice is going to send over this quantity right here, which, if you recall, is what Alice uses to pick her input wire for that key. Okay. Now, Alice and Bob. So at this point, Bob has all of the information necessary to evaluate the circuit. So someone try to convince me this is true. If you follow the protocol so far, you'll be able to figure out how you get all the inputs in order to evaluate. Okay, this is a beer question, so remember, Alice created these circuits using these keys for her input wires and the W's for Bob's input wires. So tell me how Bob is going to continue evaluation. It's not magic. It's all the information is there. Okay, so these protocols are tricky and subtle, so I'll explain this. In that previous set, Bob sent over all these KJs to say, yeah, these are the circuits I'm going to evaluate, and I only received those KJs for things that I put into the OT for which I had either this string or that string. Okay, and then Alice responds for each of these. She's going to give g to the ai xi. That's her input, and she's going to give that value. Okay, and Bob is going to record that value right here. So in the next step, Bob is just going to hash those values because that's exactly how Alice created those keys. Okay, so this is how Bob gets Alice's keys, and then for his own keys, he got those in the oblivious transfer. It's actually, this was a trick. This line should be extended to here. It's these values right here. He had yi right there and Kj for all the ones he's going to evaluate. So he's going to use this guy right here and this guy right there. Those are the input wires for both his inputs and Alice's inputs. And then Bob will evaluate. Okay. So at the end of evaluation, Bob is going to have output wires. He's going to have j output wires for every. He's going to have j strings for every output wire. And now for each of those output wires, he's going to run this check circuit. And this is a question? Yes. I know that you asked me to do the looking this way and also the staying this way, but I can't do this because I have to point there and then it's oblivious as to where I'm pointing. And so I can't, if I turn my head this way, the microphone doesn't work. So this is, one has to make compromises in life, and this is how to be my compromise. Okay. Okay, so with these output wires, he can then run this circuit. So of course, if all of them are the same, he'll just put bot for each of these check circuits and just receive nothing. Otherwise, if he has a witness for this cheating, then he will use this. Now there's one slight complication, which is when we run this check circuit right here, we are going to use a secure computation protocol. And if you read through this paper, it'll make reference to a very specific protocol. And in that protocol, all keys for wires are generated in this particular way. You basically hash this discrete log, this element in this prime order group in order to get the key. And so the keys for this circuit will be formed in a special way. We're going to use exactly, if you look at this term right here, we'll use the same AIs and the same group, etc., but we'll just use different R's. So we have here R hat here, and correspondingly the keys for this circuit will be K hat 0 and K hat 1. And so that's this slight subtlety. In order to make sure that the same X is input into the original garbled circuit and this one, we will be generating keys for these check circuits in exactly the same way, and we'll be doing the consistency checks the same way later as well. Okay, so that's step 6, check for cheating. Here is how we do the input consistency check. And so what Alice is going to do is for all of the test circuits, Alice is going to give RJ, okay? And so this is one has to put 2 and 2 together to see how. So remember, J was to set the challenge, the set of circuits that are cut. So if Alice sends over RJ for each of these things, I'm going to claim that Bob has enough information to now check all of the circuits. So spend 1 minute with your partner next to you and try to convince yourself that Bob has this information. Once you do, raise your hand and we can move on. But this is just interactive check to make sure you're following. And it's so that you'll understand this technique. It's a different way of doing garbage, of checking the cut. We're going to talk about, in the second half of this, we'll talk about a different way of doing this. There's a trick here. Remember, this is all the information that Bob has. Oh.
That's what I'm asking.
So, raise your hand if you have a suggestion. But continue talking until you do, though. Yes. You want to explain it?
AI to the RJs will give us the keys for else inputs. So we have all keys for else inputs for the cut. So we have all keys for else inputs for the cut.
Okay, I'll repeat what you said so that everybody can hear. I just want to have a query, though. Did all of you have that and just wanted to do chit-chat? Or, okay, so I do this so that if you want me to move on, just say that. But I do this so that you learn exactly the insight that's used here. So one way to check circuits is I give you all the randomness used to check the circuit. But another way, the way that's used here, is exactly as you said. With the RJ, Bob is going to do the following. First, he's going to check these commitments were proper. Okay? And then, remember that in that first message, in that step 2, this was something that Alice sent over. G to the AI and G to the A0 and G to the A1 for each input wire. So now, given RJ, Bob can raise each of these terms to the RJs right there, and basically recompute these keys. So with this term, Bob can both check this commitment and also check the input keys. Can generate the input keys for Alice. So now he has Alice's input keys. What about Bob's input keys? He already got them in the oblivious transfer. When he chose the circuit as a test circuit, he received both the 0 and the 1 key for his own inputs. So now he has Alice's inputs for both 0, 1, Bob's inputs for both 0, 1, and by the definition of garbled circuits, now you can basically check each gate and go up. Okay, so this is a kind of cool way to check the circuit. Just by giving both pairs of inputs, one can do that. Okay, good. So this is the consistency check for check circuits. The next step is the input consistency check. And here is where a sigma protocol comes in. I'm not going to go into the detail of this, but it's essentially a protocol that's going to check the following. So if Alice was using all zeros in the input, in her J input, okay, then, so remember this set right here, J not in J and J hat not in J, those are all the evaluation circuits. So Alice is going to do this for all of the evaluated circuits, and what she's going to do is give a proof that these are DDH tuples. So essentially, all of the zero wires are all of the keys for the zero wires are going to be in this DDH tuple, okay? Both for the original circuit and for the check circuit. So either all of the zero input wires are the same or all of the one input wires are the same. Okay? And this is because the RJ is used, the AI is used, it's the same AI used for all the input wires. The only difference in each of the copies of the circuit is the R. Okay? So this is a special sigma protocol that's reasonably efficient and requires a linear number of exponentiations in order to check the input consistency. Okay? And this is one way. In about 10 minutes, we're going to talk about another way to do this. And on Thursday, I believe one of the talks, Riva, will talk about an even more efficient way to do this test. Okay. So then finally, either using these output wires or the X that was recovered through the check circuit, Bob can basically send the output back. Okay? And so, what was I going to say? So again, the efficiency of this circuit, of this approach, the cost of this approach is S copies of the main circuit and roughly 120 copies of this check circuit. And the check circuit is very simple. I would like to try to give one idea for why the hybrids for this protocol actually work, and I think one of the key insights into this strategy for designing protocols that are maliciously secure is this use of this OT. So if you can think about how a security argument for this would work, what you're going to do is take the original experiment as the real protocol works and slightly modify it case by case in order to generate a simulator that produces the same output for the real protocol. And the first step in this, one of the key ideas, is to use this special type of oblivious transfer. This is going to be maliciously secure oblivious transfer, and what that means is that this protocol will modularly have a simulator that one can use in order to extract. And so when you extract from this, what you get, so if you're trying to build a simulator for Bob Star, for a malicious Bob, what you'll do is run the simulator for this particular protocol, which will extract Bob's input to this protocol. So as a result, you get Bob's Y, and you also get which circuits are challenge circuits and which circuits are evaluated circuits. And so one can do this either with coin flipping or through this particular method. Okay? And if you do it with this method, now once you have the input, you can then send it to the trusted party, get an output. And then the second aspect of security comes in. This is where you actually use the security of garbling. So as in the morning session, there was a slide describing what the properties of the garbling scheme are, that it could garble, that it can encode the input, that it decode the output, and the security property was that roughly something like this. So if you garble a circuit for some function f, and then you garble some input x, this tuple, the f, the encoded input, and the decoding bits, will basically be indistinguishable from a simulator that is only given the function and the output. Okay? So just like in this security game, what do we need to show security after we do this oblivious transfer extraction? We basically need to come up with circuits that will make Bob think that the output is whatever it is. And so what one will do is, once you know which circuits are test circuits and which ones are evaluated circuits, you'll run a hybrid where you change all of the evaluated circuits one by one into simulated circuits, circuits that you generate just by using the function and the output. Okay? So that doesn't get to the complexity of this argument. One has to take in all of this probabilistic analysis about when the input, so when this checking works. So it's a rather subtle argument, but I can only give you this level of insight as to the key features which kind of make it work, but it's a delicate argument. The one point I do want to make about this protocol, and it is perhaps now obsolete, but based on our tree story, we'll still continue and we'll wait for this Thursday, is that this protocol uses specific assumptions about the input consistency, and I've had a goal in mind to remove that and have a protocol that doesn't need those specific assumptions. And I believe you've already solved this. So this is the hole has been dug and already covered before, or the tree has already been planted. Okay. So in this next section, what I want to do is describe two more ideas. So this idea right now, we're stopped, full point. This idea that we've discussed was a novel way of doing circuit consistency. Okay, instead of doing the standard cut and choose, this was a novel way, and all of the pieces fit together in a way that gets perhaps the most practical protocol there is. So now, what I'm going to discuss is an older protocol that demonstrates two other techniques that are used to solve these other problems: selective failure and input consistency. So just as a review, what did so we're gonna now discuss another protocol idea: selective failure. Remember, this problem was when Alice inputs input wires here and bad input wires for one of the cases. Okay, and Bob won't know if his input was the correct one. So okay. So the idea here, it's going to be the idea from Lindell-Pincus, and the idea is to encode the input in a special way. So the problem with this case is that when Bob inputs just his input bit, and Alice does a selective failure attack, if there's a failure, Alice immediately learns the bit. What we're going to do to defend against this attack is to still allow selective failure, but decrease the harm of that particular attack. So we're going to make it such that Alice has to do at least k successful selective failure attacks before she actually learns anything about Bob's input. And this is again the idea of cut and choose, because we're going to try to encode our input in a way and use repetition in order to try to decrease this error. So how does it exactly work? Bob is now going to pick a new input, y bar. Okay? It's going to be a much longer input than his original input, but only linearly larger. And Bob is going to use this, and then we're going to augment this circuit so that this circuit, now this was yellow, a very pale shade of yellow, and this darker yellow is what is added to the circuit. So we're going to make an addition to the circuit which takes Bob's input, multiplies it by this matrix M, which will then decode this y bar into a y. Okay? And now we're going to talk about the special property of M that's necessary for our security analysis to work. So what we're going to do, we're going to say M is going to be a matrix that satisfies this property. It's K-probe resistant. So what that means is that if you take the Hamming weight of any subset of columns of M, any non-empty subset of columns, then the Hamming weight is going to be larger than K. Okay? So essentially, yeah. So, repeat? Oh, K-probe resistant. So it's just, this is the definition right here. So this matrix is probe resistant if you take any L columns, any set of L columns, and XOR those columns together. Okay, that's going to get you some vector. That vector has to have high Hamming weight, like a high distance kind of thing. And if you have this property, you can make an argument that essentially the probability that this evaluator is going to abort, given that the input is Y, minus the probability that the evaluator aborts given some other input, is very, very small. So no matter what the evaluator's input, the difference between any two valid inputs is going to be very, very small. Okay, so that's a technical argument that one can make from this property. But once you have that, argument, then you can, then I guess it comes to construction detail, and one can use a Reed-Solomon code, a Reed-Solomon code to produce the columns of this matrix, so that you can get a very small version of this matrix. Okay, and so that is. This is a very good black box way of dealing with this, and I'm not going to spend too much time on why this works, because I want to get to this second protocol, which will highlight a solution to this input consistency. So the selective failure can be solved in a black box way using this linear algebra, and we're going to see how that works in this input consistency argument. Okay, so here's this third major problem. In the Lindell protocol, we saw a sigma protocol approach to solving this problem, and now we're going to see a black box version of this protocol. It doesn't need to use any specific number theoretic assumption. So recall the problem of this is that Alice may use different inputs for each copies of this circuit, and we have to verify that. Previously, we used that sigma protocol. Now we're going to use something slightly different so that we get something like this. So the budget that we have to solve this problem is Kn symmetric operations. Okay. Yes. In addition to yes. I guess it's so by studying that proof from the property that one needs for this proof that all of these inputs are the same across various circuits, it suffices to use a witness indistinguishable protocol, because, and I'll say this one sentence, at a high level inside this argument, what you're going to do is change from whatever input that the real generator was using to essentially all zeros. So as long as one can come up with some witness, and the evaluator cannot tell the difference between which input was used, then this simulation argument works. So all we need is a witness indistinguishable proof for this. And a sigma protocol is a great example of such a protocol. But now we're going to look for something that's more efficient. Okay, are there better algorithms for this particular, for this equality, for this special case of checking? And the inspiration is going to be, again, this kind of, it's a recursive thing. Just like we use a check circuit, although this is temporarily reversed, this check circuit and this idea kind of came at different times, and we're going to use a different consistency circuit in addition to the original circuit in order to verify that all of these inputs are the same. And this circuit, if we abstract it, what the circuit is going to do, it's just going to compute this function g of the input. Okay, so we're going to compute the original circuit and then Alice's input is going to be diverted to this circuit, and now we're going to compute this other circuit and make sure that that these g of x, if all of the x's were the same, then g of x will be the same across all the circuits as well. Okay, and so now the question is, so the proof is just going to be, the proof that I want for this has to take this form. It has to be a function of all the different inputs. And if they're all the same, then if all the inputs are the same, then this function should also be the same. So what properties must G have in order for this to be sound and witness indistinguishable? If I have xi and I give you g of xi, and I want it to be witness indistinguishable, there should be some property. What? I would say it has to be hiding in some way. It has to hide xi. And then for it to be sound, it should be binding, yes. It should be binding in quotes, because it's not exactly the same as this other notion, but so that's the intuition. G should be a hiding and binding function, so we can obviously take some commitment of x, and if we compute this commitment based on all of these inputs and all the commitments are the same, that's a good argument that x was the same. But the problem is that a commitment scheme might have a very large circuit, so although we might win for some of these things, it's not necessarily a good solution. So now we want to find, instead of a generic commitment scheme, we want to find a more efficient one, and we discovered that this information theoretic thing, a hash function, would actually work for this. And so what we're going to do is, if we take the input x and add enough random bits at the back here, so if we augment the input space to be x and r, then this y right here is going to be hiding for large enough r. So if we add enough bits here, by leftover hash lemma, this y will be hiding. And moreover, if this range is large enough, if the range of this matrix, so if this is large enough, then for any two different inputs, as long the probability over the random choice of x that these hashes collide is just like a standard hash analysis. It should be b minus 1. It should be 1 over b, where b is the size of this range. Does that intuitively make sense? Okay. Okay, so all we need to implement this strategy is that this function m that's used to compute this hash should be chosen after x has been committed in some way. And that essentially means that for any two pairs of inputs that are committed over the random choice of m that are chosen after, this will give us the soundness that we need for this proof. So that's what this approach looks like. We compute this m of x on the side right here. And if we were to do this naively, this matrix vector product would have n squared AND gates. But we don't actually have to compute this function using a garbled circuit like this. We can actually come up with a different way to compute this circuit. And we've done that by recognizing this interesting property, that the hash function that we've chosen is homomorphic, meaning if you hash pi and you hash x, that's equivalent to the hash of x plus pi. Okay. So this property right here is going to allow us to compute this hash right here in a more efficient way. So in particular, if we have some commitments to both these x's and then x's plus pi, where these are just randomly selected here, bits, then we pick the hash function, and then Alice sends over hashes of these pi's. Remember this equation right here. Okay, we are going to have her send these and to send these right here, and that will allow us to compute those. So first she selects those, then we select some challenge, and in order to verify that she's properly committing to these values, we're going to ask her to open the random values for some fraction of them, and the So this is a check. You can think of this as a check circuit, and this is an evaluation circuit. So for the check circuits, we want to make sure that the values that she committed here are actually, she's sending the right ones. Okay, and for these, once we have this commitment right here, once we have this input right here, then given this input and that input, you can sort of see, you take these values, you compute h of this term right here, you add them, and you'll get the hash of x. Okay, so this is a special purpose protocol that we designed for computing this homomorphic function. It's a cut and choose protocol, as you see, and is what we'll use to, it's a simpler protocol than writing the garbled circuit, because in particular, how many gates do you think this protocol will require in a garbled circuit? So what I want you to compare to understand if you get the gist of this idea, not the technical details, the gist of it, I was suggesting that we just add another garbled circuit mx right here, and of course through that same process we'll cut half of them and make sure that m is implemented properly, etc., etc. That's option one. And I said that that's going to require n squared gates. I was unhappy with that, so I suggested there's a homomorphic property, and here's how we're going to compute it. So the question stands, how many gates will this approach require? It's a small integer. Zero! Yes! Who gets the second beer? Third beer? Okay, you have two. 1, 2. Okay. Good. It was a trick question. Yes, it was a trick question because I'm claiming you don't need to have any garbled circuits in order to compute this circuit. You can do it homomorphically through this protocol right here. Okay, so we're going to walk through the implementation of these two ideas, the selective failure and the input consistency, in the same way that we walk through this, the Lindell thing. Okay. Very good. Okay, setup. So this idea is going to take a different approach to checking circuit consistency. Here we're going to use these random coins row to generate all of the wires that are needed in a circuit. Okay? And okay, so row J will be used to generate all the wires of the circuit, and okay, so the labeling for wire I will be that this is the key, right? So these keys are all generated through the pseudorandomness, and the key for the 0 wire, the key for the 1 wire, and this permutation bit here. Okay, and this W is going to stand for the key and for the bit plus the permutation wire. Right? Okay, so in the first setup, X is going to augment her input with some random coins here necessary for that for the hash function. And Bob is going to encode his input using the selective failure matrix. Okay? And also Alice will pick all of these coins right here for each of the circuits. In the second step, Alice is going to send over a series of commitments that are needed in order to do all of the consistency checks and to execute the circuits. So, in particular, she's going to, all of the generator's input, she's going to commit to the 0 wires and the 1 wires using this type of randomness. Again, so these two commitments right here, the randomness needed for these commitments will be generated through this pseudo-randomly here. Okay, and So here, the generator's inputs are committed 0 wires and so in permuted order, the zeros and the ones, okay, because those are Alice's inputs, and the evaluator's inputs are actually committed in these are in the first slot will be zeros and the second slot will be all ones. Finally, Alice will also commit to her own input. Remember, she encoded her input, adding the special randomness. She's going to commit to her own input using independent randomness, this gamma I. Okay? So, as before, we're going to write on this side all of the values that Bob collects during the protocol. Bob will then send over M, the matrix used in order to commit to his, he's going to select this matrix and he's going to send it over, the one he uses to decode. Alice is going to have to incorporate this into the circuit that's used. They will then choose this H. The H function is the one that's chosen in order to do input consistency. This hash function that we just talked about, the two universal hash function, as I mentioned, Alice has to first commit her inputs, and then we have to select that function. So we'll do coin tossing in order to select that. Then we will use oblivious transfer. So we're going to use oblivious transfer twice. First, in order to get the input keys, Alice is going to put Bob's 0 wires and 1 wires. This is a standard OT. And Bob will put his own input wires in and get these input wires. If at any point, okay. And then here are the circuit OT case, okay? So just like this is, just like before we used OT, we use this cut and choose OT. This is a similar idea here, that Bob is then going to use a standard OT to either select for every check circuit, either select to get the randomness used to generate that circuit, or to use, or to get basically the openings to the commitments for Alice's wires. So these are the gamma commitments and these are the theta commitments to Alice's input wires. In addition, he's going to get the evaluation of the hash function for all of those pi bits. If you remember from so I know a lot of things are coming into, basically interlocking. And this is the problem with these protocols. They all have lots of aspects coming together. But if you recall, this is the hash of the pi used in the universal, the two universal argument is the homomorphic, the random bits for that. So if he decides to evaluate, he'll get all of this information. If he decides to test, he'll get this information. Okay, and he selects that based on that same distribution we discussed. Okay. In the next step, they do the garbling, and all of the circuits are sent over, and either Bob checks the circuits or evaluates the circuit. So to evaluate the circuit, as you see, Bob has received his input wires through the OT, that's the Y step right here, and received Alice's input wires through the second circuit OT. He receives his wires and Alice's wires so he can evaluate. In order to do the check, he's going to use these random coins in order to check all of the commitments and then also to check the garbled circuit. Okay? And in this case, if any of these tests fail, Bob can legitimately abort. This will go through the analysis of that selective failure, that the abort is going to be independent of the input that's used, and also this the particular distribution that's used to select there. Okay, and finally, the input consistency. If you remember, the input consistency is this check right here. This was received. This value was received in the OT, and this value can be essentially computed by Yes, because for all of Alice's input wires that Bob received through the OT, those input wires include this check bit. If you remember from the first slide how I described those check bits, this W includes both the key and the check bit. So given these check bits for the input wires, Bob can compute this thing right here, which is X plus the random bit, and this is the random bit, so Bob can compute this hash of the actual input, and then make sure for all pairs in the evaluation that this equation holds, that the hash of the input for circuit A was equal to the hash of the input for circuit B. And he can evaluate if any of those things are not the same. Okay, and then we use majority again if all of these things pass. So I think possibly online maybe this went too fast, but if you are interested in this, you can use these slides and a copy of the paper and sort of go through and try to learn these techniques and so forth. And tomorrow you'll see an improvement on this as well. Okay, so very good. I want to talk about the performance of all of these particular protocols, and in particular some ideas of where we can go with this. Okay, so from like 2012 or 2013, one of our best implementations could handle very large circuits for reasonable type of problems. And for a particular system, we could basically get around 650K gates per second. The garbling was much faster. Now this number is more like 1 million, based on some optimizations of this implementation. Most of the time being sent in communication. So this will be a stark contrast. So you shared these numbers with me right before the talk. When we were just running one core for malicious security, it took lots of seconds in 2013 to get one instance of this to be secure. But the point was we had a parallel implementation so that if you had enough cores, this is running in like 1.4 seconds for one AES. And the honest but curious version of that protocol at the same time was around 1.6 seconds. Now, what's amazing is that, correct me, I think based on my memory of your results, for the paper that will be tomorrow, roughly, think about this as 1,400 milliseconds. And I think what you quoted was around 200 milliseconds, is that right? Yeah, so there's a factor of 7 improvement just by changing the protocol, and that implementation doesn't require 256 cores. It requires just a few cores, and so that's an order of magnitude improvement based on a new way of doing cut and choose. So I'm very excited about that future work that through new algorithm is getting a factor of 10 improvement on this for much more realistic implementation. Actually, this was 256 cores. Okay, so what I did want to also show was that going from going from discrete log assumptions to total black box protocol was also an improvement in terms of so this shows you that removing specific number theoretic assumptions doesn't necessarily reduce performance. If in particular it could improve performance, and that's a good insight to have with all of this. And this is why I mean, perhaps you guys have done that for the Lindell 13 idea and this new protocol that's discussed tomorrow. AES-NI, I wanted to basically discuss a few ideas. Well, so this is there's a special instruction one can use. This is how we implemented it for key expansion and for the particular PRF. This is not the right way. Yuda has spoken to someone at Intel who has a better way of interleaving these with these. The experiment that I wanted to report is right here. So basically that number right there is the bottom number in this over here is the number. This tells you the number of clock cycles to do one computation here. This is roughly 221. That's setting up the key and then computing the PRF. And so this gives you the number of cycles that you basically need to compute one gate. It gives you a good metric. So roughly 1,000. You can interleave these things even more improved, but that's basically the way you if you try to do SHA, since there is no hardware for SHA, then this is going to be thousands of cycles or tens of thousands of cycles for SHA. Okay, that's great. This gives you some basic idea of the improvement. Here's the implementation of SHA. Here's our implementation of AES-NI, and you can sort of see that there's for larger and larger circuits, you get larger and larger improvements, 70 to 80% improvement based on our specific implementation, which can be further improved with interleaving and so forth. We did work with GPUs, very cursory work here. This data is very noisy because these systems are kind of fragile, but that's, the lower ones right there are the things that we improve. You can basically think of these as 35 million gates per second, honest but curious. There's much more work to do here. In particular, optimizing all of these protocols for, we haven't done a full implementation of the malicious case on this, and I think the protocols are changing so quickly. My students have graduated, so I don't have the one that is an expert of this. I'd like to find someone new if you're interested in this area. More speculatively, I would like to talk about these plans for what I think will be very good. So Bitcoin is people have invested millions of dollars in building, customized hardware to mine, which is basically computing a SHA function very, very quickly. And they have a very nice case, which is it's very low input and lots of computation. We, with Michael Taylor, who's an architecture guy at UCSD, we have come up with this block design for a particular for an approach to try to get 1 billion gates per second, and all of this speculative work was done before this improvements in garbling that have come. So this can actually maybe be 1.5 billion gates per second. This type of architecture, and this was how we would look. So we would have a little special chip right there that does a lot of SHA hashing. Instead of AES, we'd use something like SHA, and then we would have a lot of cards to do I/O, and these things are massively parallel, and the algorithms are this is one of the key ideas behind this cut and choose, is that you could create very simple hardware, which someone has already designed for Bitcoin. You can put it into a chip like this and just get the right I/O, and then this would be Alice and this would be Bob, and this could either be the internet or it could be, in this case, people that are meeting in person. If we think in the 2020s that secure computation will be ubiquitous, then it's not so outrageous for us to believe that something like this could happen. Because if you think about in 1980, it was outrageous for someone to think that a chip that Karmit gave me just 20 minutes ago, a chip that was that small could hold 128 gigabytes, and that was outrageous. And so it's not outrageous for us to think that this type of hardware could be put in that same form factor that Karmit sent to me. And then when we want to do secure computations between the two of us, we can just or we can physically touch them or do something like that and do the computation in a maliciously secure way. Or if 2 banks are meeting and doing a negotiation, or 5 banks are meeting and doing a negotiation, this type of thing is not unreasonable. And so that's where I think we're holding on this, because as we've seen in the last year and a half, there have been lots of new protocol ideas. And we're still trying to get DARPA to give us money to build this type of thing. So with that, I think, is it time for the break? Okay, so in the next section, I'll talk about this garbling work, which it'll be a little bit of review of the stuff in the morning, but with some new results. Okay.